Today we're going to look at two functional equations from the 2010 International Math Olympiad. And there's a French math YouTuber who made a video about this first one, but there's not one in English, so I thought I'd make a video about this, and I'll link the original video down in the description. Okay, so let's see this first one. Our goal is to find all functions from real numbers to real numbers satisfying the following equation. We have f of the floor of x times y equals f of x times the floor of f of y. Okay, so let's get started. So the first thing that we're going to do is set x equal to 0 and then let y be free. So I'll just denote that by saying that y is equal to y, if you will. So plugging that into our functional equation will give us f of 0 over here, kind of obviously, equals f of 0 times the floor of f of y. But now we've got an equation that we can solve for the floor of f of y. But in fact, we can't always solve it for the floor of f of y. And that's because if f of 0 is 0, then we kind of destroy all of the information in here. So that gives us two distinct possibilities. And those possibilities are that f of 0 equals 0, and thus we have no information about other values of f just yet. Or we have the possibility when f of 0 is not 0, which immediately implies that the floor of f of y is equal to 1. And that's by dividing both sides by f of 0, which you can only do if f of 0 is non-zero. So now let's do another round of substitution. And in this case, we're going to set x equal to y equal to 1. So let's see what that does inside our functional equation. So that's going to give us f of 1 over here on the left-hand side, kind of obviously. And on the right-hand side, we're going to have f of 1 times the floor of f of 1. But now we can make the same sort of argument. So observe that that immediately allows us to see that f of 1 is 0. That's one possibility for that equation. Or the floor of f of 1 equals 1. Because if f of 1 is non-zero, then we can divide both sides of that equation by f of 1. But now, putting these two things together, we have some possibilities. So observe we have the first possibility given by these two peach underlines. So if f of 0 is 0 and f of 1 is 0. So like I said, that's the first possibility. The second possibility would be if f of 0 is 0 and then f of 1 is 1. So like I said, that's a possibility at this moment at least. And then we've got a third possibility, which is if the floor of f of y is always equal to 1. But let's observe that this second possibility from our second case, lies inside of this. Now, notice I didn't really take what would be all possibilities given no other information, and that's because it's impossible for this pink underline thing to be true and simultaneously this peach underline thing down here to be true. So just to reiterate, we have three cases to check. We have this peach underlined case when f of 0 is 0 and f of 1 is 0. And then we also have, let's see, this green underlined case when f of 0 is 0 and the floor of f of 1 is 1. And then we have this pink underlined case where the floor of f of y is always equal to 1. So let's see if we can take care of a couple of these in this margin down here. So let's start with this peach one. So let's suppose that f of 0 equals f of 1, which equals 0. But now let's substitute into this x equals 1 and y equals y. So in other words, we're taking x to be fixed at 1, and then we're letting y be a free variable for the moment at least. So let's see what that's going to leave us with. So let's see. Over here, we're going to have f of y. And then over here, we're going to have f of 1 times the floor of f of y. But observe that we know f of 1 is 0, so this gives us 0. So all in all, what we see from this possibility is we have f of x equals 0 for all x real numbers. And that's because, well, y was arbitrary at this point. So just to reiterate, that is a possible solution to this functional equation leading from this peach underlined thing that we've calculated so far. So now let's look at the other two cases. So we just saw the function that's identically 0 is a solution to our functional equation. That's pretty clear just by looking at it. Now we're going to look at the remaining two cases, starting with this one. The case when the floor of f of x is equal to 1 for all real numbers x. Now, what are we going to do with that? Well, the trick here is to start like this. Let's take x to be equal to x. In other words, x is free, and we'll take y to be equal to 1. We kind of obviously want to set one of them equal to 1 because we know that the floor of f of 1, in fact, is equal to 1 in this case. And here we can use this floor part on the right-hand side of our functional equation. Okay, so let's see what we get when we plug those two things into our functional equation. We're going to have something like this. We have f of the floor of x is equal to f of x times f of really the floor, well, really the floor of f of 1. So I left that out. So the floor of f of 1, but we know the floor of f of 1 is 1. So that means we have, maybe switching the order of equality, f of x equals f of the floor of x, and this is for all real numbers x. Okay, so now what can we get out of that? Well, that means that if x is on this half open interval between integers from n to n plus 1, then we know that f of x is equal to f of n. So if we can determine the value that f takes on integers, then we're in fact good to go. So let's see how we might do that. So let's start over here with f of n, and observe that I can write that as f of n times the floor of f of y for any choice of y. Now, what choice of y should I take? Well, I think a good choice would be the choice 1 over n, because that's going to give us some simplification in here if we apply our functional equation. So let's say here we'll set y equal to 1 by n, and we'll have this is equal to f of n times the floor of f of 1 over n. But then by our functional equation, we see that that's equal to f of 1. But, well, what does that tell us? Now we can extend this off this way, and we have f of x is equal to f of n if x is on the interval from n to n plus 1. But then in turn, that's equal to f of 1. So in other words, we have a constant function. And our constant function is simply, well, whatever value the function takes anywhere, we might as well take that value to be f of 1. But we also know that if we take the floor, we get 1. So in fact, we have a constant function, and that constant lies between 1 and 2. So putting this all together, we see that we have a solution where f of x equals some constant, and that constant is on the interval from 1 to 2, not including 2. Okay, great. So let's observe now we've taken care of case 2, and all we have to do is look at is case 3. So moving on to our last case, we're going to look at the case when, let's recall, we had f of 0 was equal to 0, and we had the floor of f of 1 was equal to 1. So that was our only remaining case after we looked at our first two cases. And now we're going to start with essentially the same calculation that we started the last case with, and that was we'll take x to be a free variable, and we'll take y to be equal to 1. Now, plugging that into our functional equation, let's observe that that led us down to this fact. F of x was equal to f of n if x was on the interval from n to n plus 1. Now, of course, we wrote that in a couple more steps in the last case, but this is what it all boiled down to. but we're going to repeat it to get a different result. So now let's look at f of 1 and observe that f of 1 is the same thing as f of the floor of n times 1 over n. But then that's going to be equal to, let's see, f of n times the floor of f of 1 over n. But now let's observe that this f of 1 over n by this observation right here is equal to f of 0. But we know f of 0 is 0 by our original assumption. So that means this whole thing is equal to 0. But we assumed that the floor of f of 1 was 1. But here we showed that f of 1 had to be 0. So that's a contradiction. So that means that, well, in this case, we do not get a solution, leaving us with only these two solutions. We have this case where f of x is a constant between 1 and 2. And then we have this other case where f of x is always equal to 0. Okay, so now we're going to move on to this second functional equation. Okay, so we just finished looking at this first functional equation. Now we're ready to look at the second, which isn't really a functional equation. It's more of like a functional relationship, if you will. So our goal is to find all functions g from natural numbers to natural numbers, which we're taking to mean positive integers, such that g of m plus n times m plus g of n is a perfect square. Now, we'll start with the following claim, which will do a lot of the heavy lifting. And that is, if we've got a prime and g of m is congruent to g of n mod that prime, then m is congruent to n mod that prime. Okay, cool. Now, let's see where we can go from there. So let's notice that if g of m is congruent to g of n mod p, then what does that mean? Well, among other things, that means that if you divide g of m by p, you get a remainder. And if you divide g of n by p, you get the same remainder. So in other words, we can write g of m as p times x plus r. And we can write g of n as p times y plus r. And the important thing here is that r is between 0 and p minus 1. But now let's observe the following. And that is, well, we might as well factor as many p's out of x and y as we can. And well, let's do that. And we can call this p to the a power, and we'll call this p to the b power. And we'll say that x is not divisible by p and y is also not divisible by p. So we factored all of the p out of x and y. But what does that mean? That means that p does not divide, well, x or y, so that means it can't divide the product of x and y. We can conclude it into that one statement right there. Okay, but now let's observe what we get out of that. And that is, we get that p divides g of m plus p minus r, and then p also divides g of n plus p minus r. Now, I think that's pretty clear just by adding p minus r to both sides of both of those equations, and you'll get a multiple of p. But then an important thing here is that p squared will not divide either of these. And you can check that really case by case. In the case when a is 1 or not 1, and b is 1 or not 1. But the conclusion is the same. P squared does not divide. I'll just put either of these. But now we want to apply our functional relationship over here. So check it out. We know that g of m and then plus p minus r times m plus g of p minus r is a square. We also know that g of n plus p minus r and then n plus g of p minus r is also square. But now these two things that I'm underlining in this magenta color have this property up here where p divides into them, but p squared does not divide into them. But since these are perfect squares that are divisible by p, they must be divisible by p squared. So from that, we see that this leftover bit is also divisible by p squared. From that, we get that this leftover bit is also divisible by p. So that means that m, well, that's going to be congruent to negative g of p minus r mod p. But then that means that n is also congruent to negative g of p minus r modulo p, just by the definition of congruence mod p in terms of divisibility. And we just argued that those blue underlined things were divisible by p. But look, that means that m and n are congruent to the same thing mod p, but that means that m must be congruent to n modulo p. So that finishes the proof of this claim and really sets us up well for the next step. So what we'll use from our claim is really the contrapositive. And the contrapositive is if m and n are not congruent mod p, then that means that g of m and g of n are not congruent mod p. But let's observe that means that if p does not divide m minus n, then p does not divide g of m minus g of n. But now what we want to do is specialize this to a kind of a nice case. And that case of specialization is when m is equal to n plus 1. But of course, if m is equal to n plus 1, then m minus n is simply 1. And that's going to give us p does not divide 1, which is always true, implies that p does not divide g of n plus 1 minus g of n. So observe that this thing over here that I'm underlining in orange is always true, because a prime never divides the number 1. But since this statement over here is always true, that means that this statement over here is also always true. In other words, the difference between g of n plus 1 and g of n can never be a multiple of a prime. Well, everything's a multiple of a prime except precisely 1 and negative 1. So from this, we immediately see that g of n plus 1 minus g of n must come from the set 1 and negative 1, or maybe we'll put it in order. So let's see, negative 1 and 1. Okay, cool. And then that brings us to our next claim. And really the next claim is that we always have to pick one of those. We always have to pick 1 or negative 1. But that actually follows from the fact that we will prove that g is injective. In other words, it's a 1-to-1 function. So how is that going to go? Well, it's going to go something like this. So if not, then there are m and a, which are natural numbers, with g of m plus a is equal to g of n. Or sorry, g of m. Now, this isn't exactly what you might have seen for something not being injective, but this is equivalent in the natural numbers because any two natural numbers are separated by a natural number. Okay, but now if there are two places where this happens, let's think about the behavior of g. It can only go up by 1 and then down by 1. Those are the only possibilities. So if it can only go up by 1 and then down by 1, what we can do is squeeze the numbers between m plus a and n to find the place where the up and down happen like almost consecutively or actually consecutively. So that is concluded in the following statement, and that is there exists an n which is between m and m plus a minus 2 such that g of n plus 2 equals g of n. So we've got something like that. But now we're going to apply our claim again. So if g of n plus 2 equals g of n, then for instance, g of n plus 2 is congruent to g of n modulo, well, any prime, but I'm going to use the prime 3 just for simplicity. But then by our claim, that means that n and n plus 2 are congruent modulo 3. But by the definition of congruence mod 3, that means that 3 must divide the number 2, which is an obvious contradiction. So let's see what we know here. We know that G is injective. We also know that the difference between G of n plus 1 and G of n is 1 or negative 1. And actually, injectivity, and then that difference between being 1 and negative 1, means that it always must be one of those. That's because if it's not one of those, then you'll get one of these cases that will kill injectivity. You can just find one case where it's 1, and then the next case where it's negative 1, and you've killed injectivity. So anyway, G of n plus 1 minus G of n is either always negative 1 or always 1. But look, if it's always negative 1, then eventually you're going to get outside of the natural numbers. But that means that it always has to be 1. But if it's always 1, then our function is a linear function. And in fact, that tells us that G of n must be equal to n plus c, where c is some constant. And then from here, what we want to do is simply check that all functions of that form work, but they kind of obviously work, because if we replace this with m plus c and this with n plus c, then we pretty clearly have a perfect square. And, well, by all of our arguments, this is the only such function that satisfies this condition. And that's a good place to stop.